Hello everyone. Hi and welcome to this Geo lecture this afternoon. I am joined by Dr. Tom Perring from the University of Sheffield. And today we're going to be talking everything about volcanoes. So their characteristics, what controls their behaviour, associated hazards, all of that. There is a chat box to the side, so if you have any questions throughout the lecture, please do leave them in there and we'll have time at the end for some to address some of those. Tom is going to kindly email us his PowerPoint afterwards, so we'll make that available on the website as well. So if there are any things that you want to go back to, you can do that through the website, and there'll also be a recording of the website on the lecture on the Geo website for you to go back to as well. So welcome, Tom, and I'm going to hand over to you now. Take it away.
Great. Thank you very much, Harriet. So today I'm going to take you through volcanoes, and I've called it from inception to eruption because I want to take you on the journey from the creation of the volcano through to what we get as the end product. So there's no better volcano. Well, there are lots of volcanoes around the world, obviously, but one of the ones which is probably the most infamous or famous is Mount St. Helens. So this is my background slide for this opening slide. It's Mount St. Helens, a really important eruption in the development of modern volcanology, so the study of volcanoes. So throughout the lecture today, what I hope to give you is an overview of the following. So 3 different parts: Part A, heat and plate tectonics; Part B, volcano fundamentals; and then Part C, volcanic hazards. So what I always like to start with these lectures is just posing a simple question. So I don't expect you to answer it in the comments, but do kind of think through this question. And it's, what is a volcano? It seems like a very simple question on the face of it, but when we think about volcanoes and volcanism in the grand scheme of things, it actually can be a little bit more nuanced than that. Volcanoes and volcanism aren't just based on our own planet. They're across multiple planetary bodies in our solar system, and there are even some exoplanets which have hypothesized to have sort of lava worlds. I've seen aspects like that. So our definition needs to be a bit more broader beyond that. So, I mean, this is the textbook kind of definition you'll get from this. It's a surface manifestation of a planet or moon's internal thermal processes through emission of solid, liquid, or gaseous products at discrete surface locations. So that's the technical definition. And really what I want to draw from this is that the definition is not necessarily geomorphological, so the shape of the volcano. Volcanoes have so many different shapes and sizes and behaviors that classifying them in a kind of this is one thing and this is the other thing can be quite difficult, as there are nearly always exceptions to any rules that we start divulging. So throughout this, I want you to kind of keep that in mind, that actually we think of volcanoes, we describe them generally, but when it comes down to it, we might be kind of shoehorning things a little bit within that. So it's not geomorphological, but that does play a part in understanding the characteristics and behaviors of some particular types of volcanic eruption. So interweaved within this slide, I've got a few videos which are part of a mini documentary I'm putting together. And I like doing this as part of some of my presentations and talks, and even put them in some of my lectures at the university as well, because it kind of embeds what working and experiencing a volcanic environment is like, which for me really helps put everything in context. Field work and visiting places is so valuable in our understanding of the environment and the surface processes which shape it. So really, I just want to highlight the aim of this. I really hope I cover the common GCSE and A-level content for you, but I also want to provide you with that little bit extra, maybe a little bit more context, that you can go away and really think about how much more there is to the topic of volcanology, and maybe give you an insight into some of the things that you may study if you were to go on and do geography at university, which of course I hope many of you do, because it's an awesome subject to study. There's no subject like it which can really entail some of the social, the physical characteristics that we need to really solve our pressing problems in the world today. But I can tend to digress, so I hope I don't do that too often. So let's kick off with heat and plate tectonics. So here in the background, this is the lava lake at Messiah, and it's no better place really. Well, other lava lakes, I suppose, but what is one of the best places in the world to really highlight that heat and the generation of heat at a volcano, and the vital aspect that the heat generation mechanisms within our planet have in our generation of volcanic activity, and varying how things appear at the surface. I mean, peering into these lava lakes is almost like peering into the center of the earth itself. Obviously, it's not quite like that, but it feels like that. It's very primordial. So when we think about volcanism, the first thing we need is some way of generating heat. Now, this is done in two main ways. So we need heat to generate volcanism. It's a simple fact. So there are two main ways here. The first is radiation. This is how we generate volcanism in our own planet Earth, and that's much like liberating heat through a nuclear power station or a bomb or similar. It's the decay of radioactive isotopes that occurs in the core of the planet, and that recycles, as we'll touch on in a moment. The second is this, and this is tidal forcing. So any of you who have an interest in planetary science, this is one of my favorite places in the solar system. This is Io, and this is the volcanically active body which orbits Jupiter. And acting on this, there are something called tidal forces. So we know that when the moon orbits the Earth, we generate a pull on the oceans, and that generates our tides. But we also get a minute effect on our surface as well, so that the more solid aspects. And this is far more prominent on larger planetary bodies such as Jupiter, which has a far larger gravitational pull. So as that orbits round Jupiter, it gets kneaded a little bit like, so if any of you have ever made bread and you knead it, you know that it warms up as you knead it. And if you warm something up, you are generating heat. And it doesn't need to be that much heat to generate volcanism. So tidal forcing may play a role in some of the generation of heat at some of the icy bodies. And that's really important, because volcanism isn't just a rock-based thing. It can be an ice-based thing as well. We can get ice-based volcanism. And it's a really key way that we can generate heat to generate the volcanism we see at the surface. So if any of you have Play-Doh at home, you've got younger siblings, like I've got a couple kids, and they love playing with Play-Doh, just get some Play-Doh and knead it around, or I've got some science putty here, and just knead it around. You can see that it warms up. We generate volcanism in that particular way as well. So that's the first thing we need in our recipe for making a volcano from inception. That's how we generate our initial energy to create a molten material, which might then ascend to the surface. So obviously, when we think about the planet Earth, we need to transport that heat then from the core, the center of the Earth, up to the surface, so that it can be released through volcanism or whichever locations we have. So when we generate heat in the interior, we need to lose it somehow. And there are a few ways of doing this. So the first is conduction, and that's heat just traveling from the interior and then straight through the crust without any kind of extra release through volcanism. We get convection through mantle plumes. So I'm sure you're aware of hotspot style volcanism, which derives the island chains of Hawaii and the activity at Kilauea and Mauna Loa. And it's these which rise from the core mantle boundary, much like a lava lamp. So you've seen lava lamps generating these blobs of molten material which rise to the surface and then they kind of overturn and back again. That's much like a mantle plume. And then the final one is through plate tectonics. So if you've ever done any sort of experiment in science, for example, looking at convection, if you put a cold bit of water onto a Bunsen burner, you'll heat the water, that will rise and then overturn. You can do the similar thing by adding different colored dyes and different warmths of material within that. And I just want to show you here, this is a really classic experiment. So hopefully it starts here and I don't freeze up. So let's just go for no laser pointer. So here we go. And this is one of those classic experiments that you may do at home or in science class at school or even in geography, where you're mixing bicarbonate soda with vinegar, and the vinegar here is mixed with blue food dye. So what happens when you do this is that you generate the bubbles which rise to the surface, and we can think of these as our kind of mantle plumes rising to the surface. And you look carefully, you can see convection cells occurring within this, where we've got sinking more dense material towards the center. So if I just play that through again, you should be able to see that nicely. And what the gas is doing here is it's generating less dense material, sometimes incorporating our kind of proxy magma here, our vinegar mix down here. What we get is our system which generates volcanism on the planet Earth. So if you fancy giving this a go, there are lots of tutorials to do this online. So that's how we generate that movement of that heat from depth to the surface through these convection type methods. So it's one thing to generate the heat, it's another to transport that to the surface and then erupt through those very common features that we are aware of. So this is one of the most amazing animations I see. I'm just going to click on it here and drag this across to the screen. So hopefully we can see this now. And this is just a map of earthquakes, volcanoes, and sulfur dioxide release. So volcanoes release sulfur dioxide during eruptive periods, so very large eruptions and consistently as well. So this is measured during our satellites. You'll see that you don't see sulfur dioxide appear until the late 70s when satellites start to measure it from space. Obviously, we can measure it from the ground as well. But I'm just going to kind of zoom this forward a little bit. And once we see this, you can see that we're starting to map out the locations for the volcanoes that we see on the planet Earth based on our plate tectonic boundaries and some of the other locations that we can see volcanism on the planet Earth. So this is great visualization from the Smithsonian Museum. Do revisit it to take a look at what happens through time. But what I'm particularly interested in showing you here are where all the locations of the red triangles are. So our volcanic activity, where we have our different type of margins. So we have our subduction zone areas here. We have our constructive areas here, so where we have our active sleeve force spreading, and you'll see that we do have kind of volcanoes in some of these locations too. But we also have volcanoes in really interesting locations. So we've got Yellowstone around this particular location. We've got Hawaii here. These are our hotspot locations related to our mantle plumes. And then if we look even more in detail at this particular figure, we can start to see some really interesting features prop out. So if we just see where my pointer is here, and we see some volcanoes pop up here. So if I hold down there, we've got Nyiragongo. So it's made it into the news recently from the recent eruption, and other volcanic locations here, Oldonyo Lengai in Tanzania. These are active volcanic locations on an active rifting systems. This is Rift Valley based volcanism, and eventually these will spread apart and form a new ocean in between, most probably. So what we have here are varying different range of locations for where we can get volcanic activity occurring at the surface. So what I want to do is now go into where these particular volcanic locations are, and how we might term and generate volcanism at these particular points. So the first you might see is the constructive plate margin. You may see this referred to other names, spreading margins, for example, because it's related to C4 spreading in the middle, where we have convection currents present in the mantle. Our crust rises, our magmatic mantle rises to the surface, erupts at the ridges, and this continued addition of material here drives this spreading. And this is our ridge push. So you've probably heard ridge push and slab pull. So we have our ridge push here, and on the edges of this, we always have something subducting on the other side, be that ocean to ocean subduction or ocean to continent subduction. We have our slab pull down here. So this is our constructive plate margin, where we have our rising mantle material. We generate magma at our ridges, and generally this occurs completely underwater. We don't physically observe it occurring often, but it has that really important feature of spreading those throughout the distance. And we know this occurs because we can look at magnetic striping on the plates mapped, and we can see that it matches up with polar reversals. And by doing that, we can get approximate ages for how long and the rates of spreading as well, which helps us build up the puzzle of where all the tectonic plates have moved through time. So in this particular locations, this is where we're generating our basaltic styles of magma. We are not really generating any kind of large explosive activity. It's the least dangerous that we'll see on the planet Earth. So our next type is our subduction zone volcanism. So, this is kind of leading on from that last one here. We've got our constructive plate margins. You might also see this referred to as a destructive margin or something similar. But this is where subduction zone volcanism is generated at this particular location. So again, it can be the collision between oceanic crust or oceanic crust, which will form our island arcs, and Caribbean islands, island arc volcanoes. And commonly also we've got our subduction of oceanic crust beneath continental crust as well. So what we can do here is we can begin to see what happens when this subducting plate is moved beneath this particular area here. So subduction is all to do with the density of the plate. The oceanic crust is more dense, so it will essentially be pulled beneath the continent here. It's our slab pull. And at a certain depth, the subducting plate releases water. And what the water does is it changes the properties of the surrounding rock or mantle such that it melts at a lower temperature. And that melting then generates magma batches which ascend to the surface. So it is that which generates this molten material, which will then periodically store within the crust, and you might have large residence times between eruptions at particular locations. So this generates some of the largest explosions we can see around the world. And of course, we have our continental based stuff as well. So this is one of our other locations here. This is an intraplate location, but this is intraplate through oceanic crust. The intraplate through continental crust is a little bit different, and you can get far larger explosions from those particular events, which we'll go through in the next slide. So in this particular instance, the hotspot volcanism is related to that ascending mantle plume, and over time it will burn through the crust and will generate very characteristic shield volcanoes and shield style morphology at the surface. So over time we generate these very large features. Now, one of the most famous shield type volcanoes in the solar system is Olympus Mons, and the difference between the volcanoes there and the volcanoes we've got here is that the tectonic plate is moving across the surface of this active mantle plume, and that will generate essentially a series of islands moving through time. And if you ever look at bathymetry or kind of models of measurements of the height of the ocean floor, you can see moving quite nicely along with the movement of the plate, and it even has this weird like kink in it. You can see how that has happened through time, and the older edifices have been eroded away through the action of the atmosphere and the oceans, etc. So this is our shield volcano, and this is where these are very active locations commonly associated with our lower explosive styles, lava flows, which are more fluid. And we'll get to that a little bit later. So the next thing I want to go into is the formation of very large calderas. So this can occur at subduction zone settings as well. It's also common. It also can occur at our hotspot locations, but where we have a hotspot within a continental setting, as we do at locations that, the most famous location at Yellowstone. So what we have here is we have, very large magma chambers. We might have something which looks somewhat stratovolcanic in nature, but it may not be. And we have a magma chamber or magma storage zone. And in volcanology, we like to kind of call them mush systems a little bit more now. And that during eruption, we have magma which is feeding that particular eruption there. And then what happens through time is that eruption ends. And this has been this is kind of an exaggerated version of what will happen, and this makes it look like a magma chamber is empty because my art skills aren't amazing. But what we do have here is an area where there was a lot of eruptible magma that has now exited, and we now generates kind of what we call an overpressure. There isn't too much pressure for what was previously in that particular area, so we don't have big empty pockets. But we see these collapse features around here. And when we collapse, we form calderas. And these are the evidence of our very largest explosions on this planet. Lake Taupo, areas such as Toba, Yellowstone. These are our largest eruptions that we've recorded. Not the largest, but there are some of the largest. And within these, caldera lakes can often form. So in essence, those are our kind of main locations for where we see different types of volcanic activity. Our constructive margins, our destructive margins at our subduction zone settings, our hotspots in a continental setting, and our hotspots in an oceanic crust setting. They will all lead to different styles of volcanism. So these are rough guides to that rule. So what I want to do now is kind of build on that and go into what I call the volcano fundamentals, the types of magma, the styles of activity that we see. And I want to give you a bit of new information here as well. And that's quite frankly related to what I study as a volcanologist and what I'm really interested in. So it's always good to kind of show you that. So this volcano here is Yasur, very low profile volcano. So what I'm going to do here is I'm going to show you a short snippet. You've heard me talk for a little bit, so I'm going to show you another short snippet of me talking. But this is, for me, what's amazing about visiting volcanic locations. Part of the excitement of fieldwork is the anticipation of visiting and discovering the environments of our world. As a volcanologist, there is nothing more powerful than seeing the evidence of subduction in the form of chains of volcanoes in the landscape. This is Pacaya behind me, and we can also go on a little bit of a walk and we can see some of the other volcanoes in the background as well. And actually, unfortunately, today we've seen these volcanoes more than we have the summit of Pacaya over there, the active volcanic cone. So Tom's chilling down there whilst we wait for some good activity. Hi, Tom. So over in the distance here, I've got to get this right, it's all backwards. So the larger cone there, that is Volcán de Agua. And then If we move over here, we have Fuego, and we've seen a fair few explosions from Fuego. Great, so that was our example there of some of the very most characteristic volcanoes we see. The picture perfect volcano, and there's none more picture perfect than Mount Fuji here, a stratovolcano in Japan. So these are built up of layers of viscous lava flows and pyroclastic rocks, and because they're more viscous, so that means essentially it's more resistant to flow. I always like to compare it to common everyday fluids that we have around. So water would be an example of a low viscosity fluid, and something like tar or honey would be an example of more viscous lavas or more viscous fluids. So essentially what that means, if you were to get a table and you were to just pour some honey on the table, that honey wouldn't spread out very far. If you were to pour something like olive oil or pour water on a table, it would spread out far further. And the more you spread out, the more you add on to the surface, the more it will spread out. So that's the key difference between the types of viscosity of fluid. And it's the same with stratovolcanoes. So if we have viscous lava flows and we have pyroclastic rocks, maybe generated through ash fall or pyroclastic density currents on the flanks of that particular volcano, then what they will do is they'll be constrained to the summit area far more, and we will generate these cone-like features, some of the most beautiful locations on our planet. And then, of course, the other classic geomorphology that we have is our shield volcanoes, and our layers of more fluid lava flows spread out a little more. And this is a bit more difficult to capture in an image than the very characteristic and lovely to look at stratovolcanoes. I mean, it's almost a perfect cone shape there. Here we have the example of Fernandinha volcano, a shield volcano of the Galapagos. And this here is the summit area at Hawaii. And essentially, you can see that by zooming in, you can see the collapsed caldera area of this particular summit area, which is very characteristic of a shield volcano. You'll have some kind of crater summit area, and it'll spread out over longer distances. I like to think of shield volcanoes as an upturned bowl, and our stratovolcanoes are very, very clear cone type shape. So that's our classic geomorphology. Now, I'm not going to get into the nuances of different morphologies in volcanoes. That's what I go into in my level 3 classes a lot, far in between. We get fissure style eruptions, we can get monogenetic eruptions, which just have kind of single eruptive vents and generate things called scoria cones. But if you're interested in that, I can kind of go into that in more detail or point you in the right direction. So we've got the two different styles of broadly two different types of volcano, our stratovolcano and our shield volcano. There are obviously kind of additional aspects around that. But we can then start to look at the types of magma we have and how those map onto the key types of volcanoes we have. So these aren't hard and fast rules. You can get basaltic magmas at stratovolcanoes as well. And volcanoes can change their behavior through time as well. I always like to think of volcanoes as having their own personalities, and that personality can change through time as well. So sometimes it can erupt basalt, sometimes it might be able to erupt more viscous magmas, and that will change and the behavior will change. So there's no one hard and fast rule, but this can help us understand a little bit about the features that we see. So our low viscosity magmas, commonly mostly basalts, these are produced at mid-ocean ridges and hotspots. So not exclusively, but most commonly. And these are the magmas that create shield volcanoes. These are the low viscosity magmas that create the Hawaii type volcanoes from that island chain. If we just take a look at this here, this is an active lava flow at Pacaya, and we can see that, and we have our relatively fluid lava within that particular area. Then we get a nice zoom of that particular location as well. So thanks to the drone pilot Alejandro for capturing this. And then we have our high viscosity magmas. So these are ones which are more resistant to flow. Because they're more resistant to flow, they generate our larger explosions. And we'll look at the cause for that in a little bit. Commonly, these are andesites and rhyolitic magmas. We also have daceites, and there are all sorts of different naming terminologies in between that as well. And these really are most commonly produced at our subduction zone settings, not exclusively, but most commonly. And these magmas create our stratovolcanoes. And you can see the eruption of this style of magma, what this kind of style of magma might lead to in an eruption size, something which is far more ash rich and isn't generating those very fluid type magmas at those particular locations. So that's an example of Shinmadake in Japan. So what controls the viscosity of a magma? Well, the viscosity is determined by something called SiO2 or silica, which is present. And it looks a little bit like this if we were to break it down into its atomic form, where we have one silicon atom surrounded by 4 oxygen atoms around the outside. And what SiO2 does is it polymerizes it, so it joins together into something called silicate tetrahedra. And what these do is they impede the flow of a magma, making it far more viscous. So the more silica we have within a particular magma, the more viscous it's going to be. And we can map that on quite nicely to the types of magma we have. So here are some really rough guidelines. So don't kind of note these down as the exact boundaries. These are just approximates for the type of magma we have and their approximate silica contents. So you can see that as we increase the viscosity from basalt through to andesite through to rhyolite, that we have a higher silica content within that. So higher silica equals more viscosity. So we've just covered the different types of magma and what controls viscosity. But a magma is not just molten rock. It is a real mixture of different things. And this kind of slide shows you that it's a mixture of melt. So it's a molten portion of rock. We've got crystals, which are solid portions. And then we've got the most important thing of all, in my opinion, is the gas bubble. And this is the thing which generates volcanic activity at particular locations, and it is the real driver of explosive processes. And we'll get into this. So I'm just going to try and show you right now. This is a rock eye. This is a magmatic rock, and hopefully we can see it there. And we can see some of the features within this here. So this was generated at a basaltic volcano, where we have the molten portion here, and we have the white crystals within that. And I have another rock here, which hopefully you can see the gaseous portion within it as well. So how do we know this is the case? Well, we can measure the gases coming out of volcanoes, and we can also see the evidence that they're there within our rocks as well. So I can always fit my finger in this one. That is an evidence of a gas bubble, nice spherical depression within that. So a magma is a common mixture of melt, crystals, and gas. So how does our gas behave? And what happens to it during ascent? Well, I'm going to take you through the journey of someone called Bob the Bubble. And Bob is born in a magma storage area, a magma chamber at depth, as batches of magma begin to ascend, and they'll essentially allow the release of gases from within them in a process called exsolution. They can only hold certain amounts within them. And what that bubble will do is it will rise from depth, and it might begin to change shape. So this is the example of a basaltic magma, where bubbles can expand far more easily and join together with other bubbles. And Bob, again, we'll run this through again. He's born within a magma chamber, and Bob is composed of different types of gas: carbon dioxide, sulfur dioxide, water vapor are the most common among some other examples as well. And then Bob will essentially combine with other bubbles or anything to rise to the surface. So here we see him transitioning through different kind of morphologies to generate a strombolian explosion. So thank you, Bob. But then what I want to do when I ponder what's going on in the world, I like to look and stare into my beer. And this kind of really nicely highlights what is happening with this particular, within a magma chamber. So we saw the example of one bubble there, and Bob's composed of different gases, and he will exsolve from a magma at a certain depth, and different gases exsolve, so come out of solution of a magma at different depths. And it's not just one bubble. I think that's what I want to highlight with this particular slide. And whenever I drink a pint of beer or see a bubbling glass of mineral water or Coke or whatever, I often think of a magma chamber. And the style of volcanism we see and how the bubbles begin to interact together is really drives the style of activity we see at the surface. So in this particular example, we don't have that much gas. It might generate a foam at the surface of this beer, but it's not going to generate explosive activity. If you were to have a go of putting a straw into different viscosity fluids and blowing bubbles in them, you'd see how easy it is for these bubbles to interact and flow during the ascent. So the next question we need to ask really is, how easy is it for bubbles to join together? If it's easy for bubbles to join together, we're probably in a basalt, and we're going to generate our low viscosity styles of volcanic activity. If it's not easy for these bubbles to join together or coalesce, they're probably in a high viscosity magma, or there's not enough gas supply. When we get that, we tend to collect bubbles on the surface of magma chambers, or collect bubbles even towards the top of magmatic conduits that link these storage zones to the surface. And what we can then see is that we want to build up pressure, and that's where we build up the very large ash generating volcanic explosions. So I just want to play you this quick video again here to show you an example of this in the field. Background, hopefully we can see Yasur volcano. There it is, right over there. That's why it's such a good measurement position up in our tree house up here. So Yasur is famed for its very regular strombolian explosions. These occur, seem to be from every 30 seconds to 2 minutes, 3 minutes. And look now, I've just timed it right. We can see a little bit of ash popping up from one of these explosions there. So these explosions, these strombolian explosions, are driven by the accumulation of gases, which create these really large gas bubbles. So we're talking lengths of hundreds of meters, and kind of widths of 2 to 3 meters, and we call these bubbles Taylor bubbles or gas slugs because they're shaped a little bit like bullets. For me, strombolian explosions, which are hosted at volcanoes with our most common magma type, basalt, are a fascinating subject to study. In some locations, we have one vent and infrequent explosions, perhaps separated by hours. In others, we have multiple vents, with each exhibiting explosions at rates of tens of seconds to tens of minutes. Given that these explosions are driven by large gas bubbles, one of the ways we can understand and compare strombolian explosion host volcanoes is by measuring their gases. So that there just highlighting the real importance of understanding gases and gas release for that particular style of volcanism. So this then leads us to our main basaltic styles of activity, and the approximate size, this is all not to scale, but the approximate size of the bubbles here kind of exhibits the styles of activity we see with basaltic volcanism. So we go from passive degassing, which is just the quiescent release of gases to the atmosphere with no associated explosive activity, or little, and that can occur through conduits, fractures and fumaroles, or through lava lakes. We then have our strombolian style activity, which we just heard about, and then we have our large Hawaiian or fire fountaining style activity. We can also get volcanian activity as well, and that's where we generate a cap along the surface, a little bit rarer with basaltic styles of activity, but it can still happen. And essentially, we tend to generate Hawaiian or fire fountaining or lava fountaining, where we have a very large supply of both magma and gas, which ascends to the surface rapidly. So it really is, if we think about looking at this on the scale of amount of gas within the conduit, this would be the most on this particular area here. Then different things happen again when we add ice into the picture. So think, I think you might have it referred to as E16 or Aya or Ayafitlo in your kind of GCSE level materials. But here, when we interact magma with ice, we can generate very different styles of activity. If you think about you've got a pan of hot oil. I wouldn't suggest doing this. You've got a pan of hot oil and you accidentally put some water in it, then it will spatter everywhere. It's a little bit like what's going on there. So it's a little bit extra for you. So what I do is I'm really interested in linking up our gas emissions at the surface with what's going on at depth, particularly in basaltic magmas. So because basaltic magmas have low viscosities, they allow the formation of really large bubbles from cap bubbles. These ones here, which look a little bit like caps, and slugs. Our gas slugs are more bullet-shaped ones. And for me, this is really interesting because we can begin to link up what's happening at depth in the form of what we call these flow regimes and the amount of gas within the conduit. So at 0, we've got completely magma, and 100, we've got completely gas. And we can map on what we see at the surface by measuring the gas with what's happening at depth there. So before I move on to silicic volcanism, another little clip of me in the field at a different location, Sabancaya in Peru.
I'm up at Sabancaya, and that is Sabancaya degassing in the distance. Woo! Over there, and now I'm hoping I've timed this video really well because it's been exploding every about 20 to 30 minutes. These explosions have been quite ash rich, and they're sort of characterized by sort of an initial increase in what looks like steam, and then one burst and then another burst. And it's really hoping, there you go, I did time it well, so we can see some ash coming out of there right now. Oh, my finger pointing is always terrible. So we should be able to see some ash coming out of the summit right there, right.
Great. So, I mean, it's difficult to see from this distance, but this is an example of one of those ash-rich style volcanoes, which generates a very different style of activity. So that's probably more kind of volcanian in style, which is across many of them. So this graphic here shows you that higher viscosity magmas tend to restrict gas flow, and that can lead to pressurization and the largest volcanic explosions. So one of the common features you may see at the most high viscosity volcanoes is something called a lava dome, which is essentially just the surface of the conduit, which is poked up a little bit. Now, if the gas is able to be released at the surface here through fractures, or you can see the evidence through fumaroles at the surface, driven by networks of bubble trains within a high viscosity magma, then we're okay. We're in a situation where things are less likely to happen. But then we can get the situation where there are no escape routes. There's no escape route for the gas. The gas will pressurize that system, and we generate our very ash-rich style explosions, which generate our ash clouds and potentially pyroclastic density currents, and our most dangerous hazards. So it's a really important feature of volcanoes. So I'm just going to have a quick interlude here. So those were the volcano fundamentals, the different types of magma and where we might find them, and the common landforms that we may have. So this is something that helps me and I give to my students to help them understand all styles of volcanic activity across the planet. So these are the key factors which control style of activity and how the activity may behave in the atmosphere and how it is generated. So it's an acronym I put together called MAGATH. And the first thing you need with volcanic activity, you need some kind of material, be that molten rock, silicate-based volcanism as we have on the planet Earth, or be that ice on other planetary bodies we have throughout the solar system. Commonly, we then also need available volatiles or gases. How are we going to generate that explosive force? We often need gases. I refer to this as available volatiles. Gravity is then a huge driver in how related things then behave. So planetary bodies such as the moon or Io have very low gravities, which means we get very large eruption columns. So, you know, Io, I think, is more than 100 kilometers or something like that, really huge eruption columns. Whereas on the Earth, this is constrained by gravity and also atmospheric pressure. So we've got some kind of constraining boundary around an eruption column. And these two things are really important in generating some of the most dangerous hazards we have, our pyroclastic density currents. And by way of comparison, Venus has a very high atmospheric pressure, which makes some of these features a little bit more difficult. So a little bit more difficult to generate. We then have our tectonic environment, so be that constructive area, hotspot, etc. And we then have our heat generation mechanism, be that via our radiation, our radioactive decay, or our tidal forcing, our tidal heating. So there's a mini interlude. I find it really helps, and if you kind of look at my blog, then you'll be able to find something on that. So part C is a shorter little section on volcanic hazards. I'm going to touch on a few of these, and we see a very large ash column here, presents very obvious local hazards. But I'm going to show you a brief video first from some more really local hazards at a particular location. I want you to think about what happens here if we've got tourists in the particular area. Volcano tourism is very attractive for a number of reasons, but it can also be quite controversial because of the dangers involved.
These strombolian explosions which happen out of this near crater here, they can throw material up really high into the sky, and it's important that we track where those pieces go. So I've got lots of video of the location. You might have even seen a shock wave there, and you can see material maybe above Tanuka flying up in the air. She's keeping an eye on where those bits of material are going, because they can come up and land on some of the terrace areas which are below this.
So that's an example of a really local hazard, which may be a danger to volcano tourists through, or even volcanologists themselves. And you can see some of the very largest bombs which do reach out into the crater terraced areas of some volcanoes. So when we think about volcanic hazards, we've got very local to more medium base hazards, and we've got even global hazards from the very largest explosions. So this is the key graphic created by the United States Geological Survey, which gives an overview of some of these hazards. And I'm sure you've seen something similar to this before. And we've got a varying array of different hazards here, which create a very different array of risk at an individual location. So we've got our eruption columns, which can be a danger to aviation and potentially the climate. If they inject gas and ash into to a high enough altitude, they can affect global climate, as Pinatubo did after the eruption in 1991. We have our tephra, which can be far more localized, and on a short-term scale, it can be quite dangerous to locals in the area, very hazardous to breathe in. It can destroy crops. There can be long-term benefits to ashfall through fertilization of soil, but the short-term aspect of that can be quite dangerous. We then have the collapse of a lava dome, which can generate eruption, which can generate pyroclastic density currents, or the collapse of an eruption column itself to generate these, as maybe the force driving the eruption column to move up wanes, or there's some kind of fluctuation. We generate these very active pyroclastic density currents, and we'll see a video of that in a moment. We can see the collapse of a volcano in a debris avalanche, commonly also called a flank collapse. It's happened during the eruption of Mount St. Helens in the 80s. We can see the mobilization of ash to form lahars, particularly important when we have very large rainfall, or we have an ice-capped summit of a volcano, or lots of snow on a volcano. When we get an eruption, that can melt very quickly and generate lahars. So that occurred in Some of the most infamous events in the past, Nevada de Ruiz was sadly one of the most devastating volcanic events to occur because of lahar. And lahars don't necessarily need to be generated during an eruption. They can be remobilized. So lots of ash deposited, very heavy rainfall, and they can be reinitialized. We can have tsunami. Krakatoa in 1883 generated tsunami and again, unfortunately, a very large death toll. Volcanic gases. Areas like Hawaii can be pretty prevalent to this. So it's something called volcanic smog in that particular location, or VOG. And these can combine in the atmosphere and transform into some pretty harmful sulfate aerosols, which are unpleasant to be around. We can then also get really interesting hazards at subglacial locations, Yokulalps, through rapid melting and outburst floods. So it's these pyroclastic density currents which are some of the most dangerous, and these happen at our most explosive volcanic locations. Gas can't move freely within a magma. It can find it difficult to escape. When gas can't escape, pressure builds up, as we have in this particular situation here, leading to the very largest pyroclastic explosions, Volcanian, subplinian, plinian, and even ultraplinian in the very largest examples. And this is where pyroclastic density currents are their most dangerous. And this particular is a famous image from the eruption of Pinatubo, and these people in this car, I believe, were lucky to survive this particular pyroclastic density current. They travel very fast and they're very hot, traveling down the flanks of a volcano. So this is a collection of films by someone called Volfilm, and I'm just going to play it quickly just to show you what these look like. They're very fast moving, and they are the most catastrophic hazards. You've probably seen these referred to in the eruptions of things like Vesuvius and their role in that AD 79 eruption engulfing Pompeii, Herculaneum. You can see the very rapid movement of these hot clouds of ash, gas, and rock in kind of this caterpillar-like motion over the summits there at the different speed. You can see the different speeds of various things at an individual location. And then we have our lahars in this particular video, and again we can see how rapidly they move along the flanks of this particular volcano within existing river channels commonly, but you can see their high energy really allows them to carry very large bits of material. If you're caught in this, it can set very quickly like cement if it stops, and it can overwhelm things very, very quickly. So before, I'm starting to round off the talk now. So just a couple notes on why volcanic hazards are really important to understand, and studying volcanoes is quite a difficult science. And if we look at the common, we've got precursors here, an event over here. We've got precursor of decades to hours, an event lasting of hours to decades. We can see typhoons and hurricanes. We get days to hours warning of where they might be. Flooding, we can get a little bit of warning. Earthquakes, very few precursors if at all. And tsunamis are pretty much the same. But when we look at volcanoes, this is the Phlegraean Fields, this is St. Helens, this is Kilauea, we can see that precursors are really variable. So we've got anything between decades and days in a certain location, or weeks to months, and then the event can last anywhere between hours and decades. So really understanding what's going on can be quite difficult at a volcano, because you don't know how long you've got to react to anything. And this is where responding to risk comes in, and you'll see this, or a similar form of this equation, where we've got risk, and risk really depends on hazards. What hazards do we have? What's the intensity? Is it a large eruption which might generate pyroclastic density currents, or is it a small eruption which might only have localized effects through volcanic bombs in the summit area? How exposed is this? Is it a remote volcano where no one lives by, in which case there is almost no exposure? How vulnerable are people or assets in that particular location? Do you have a hydroelectric dam? Is there an electricity generating plant? do a large number of people live in that particular location? And then I like to kind of overview all of this with capacity. What's the resilience? What's the ability of people to respond to a particular hazard through putting up of concrete kind of shelters at the summit of a volcano, through to just preventing people from accessing it, through to, well, if you're a rich enough nation, you can just persuade people to live elsewhere. So that's all related to the capacity or the ability of people to respond. And this again is one of my interests. We can then really reduce risk through monitoring. We can study gas release, seismicity, the deformation of a volcano, how much heat a volcano might be putting off, to really determine what happens at Y. And what happens at Y is our eruption. That's what happens. We want to determine what happens. And all of these individual data streams add up to determining that. And through doing things like that, and this is an example adapted from, inspired by Willie Aspinall, who's at the University of Bristol. And this is the example of Montserrat volcano, one of the most monitored volcanoes in the world. This is on the island of Montserrat. And this is to forecast dome collapse. So I should have said in this previous slide back here, we like to call things forecasting rather than predicting, because forecasting has an element of probability attached to it, which prediction doesn't. You're going to say it's going to erupt exactly at this date and on this time. So what we can do is we can try and forecast dome collapse by building up some of the important aspects which might lead to it. So we have a lava dome here. And we want to know how stable it is, because if it's unstable, it might lead to its collapse and the generation of pyroclastic density currents down the flanks. And we can feed all sorts of information into that based on our measurements of things like ground deformation, seismicity, to determine whether magma is moving at depth, whether we've got pressurization, and whether we then eventually get stability. And any external forcings we may have on that as well through rainfall on the dome. So again, I'm not going to go into this in a lot of detail, but you can see this in the slides which will be uploaded. This is taken from the History of Volcanology and the Encyclopedia of Volcanoes. But it's some of the most important and largest eruptions, not necessarily largest, but the important eruptions which have kind of shaped our understanding of volcanism, volcanoes, risks and hazards. So do take a look through that and think about how what I've talked about maps onto some of these very large or very small eruptions and how they had such an impact at the time they did. So you've got to really keep a temporal context in one of these. Santorini here, a very large explosion, may have led to the decline of a whole civilization, through to Pinatubo, which was one of the largest eruptions of the 20th century and had major impacts in the Philippines and could have affected the atmosphere more widely. So that's my lecture for today. I hope I've taken you on a whistle-stop tour through those different parts: heat, plate tectonics, volcano fundamentals, and the volcanic hazards, and how they begin to link together with each other. So thanks very much for listening, and I think there is time for questions. I think, Harriet?
Yes, we do have some time for some questions if anyone has any. Obviously, if you're watching the stream afterwards, still feel free to leave your questions and we can pass those on to Tom at a later date. Let's just have a look. No questions at the moment, but that was really great, Tom. It's so interesting to see those videos, particularly of live eruptions, because you always see the quite over-dramatized, lots of lava, but you don't always see the sort of gas coming out, and it's so interesting to see it happening in front of your eyes. So that's really useful.
Yeah, I think often the common question I always get, you meet people generally, oh, I'm a volcanologist. Do you wear the heat suit and get really close to lava? And very few people actually do that because it's a crazy idea.
Yeah. Well, we don't have any questions, I don't think, today, but I hope that that's... Oh, okay. Well, no, we have one. Yesterday, I found out some volcanoes produce blue lava. Can you talk
Mhm.
more about how this might happen?
Yeah, so if I'm not mistaken, I think you're probably referring to the sulfur-based activity. So there are some locations around the world, I might be wrong here, I hope I'm not, that they mine things like sulfur, and when you do that, you can kind of ignite and you get sulfur-based eruption. So I'm pretty sure that the blue lava style is sulfur-based activity.
Okay, great. Yeah, so it's a chemical sort of
Yeah.
reaction. Great. Well, if you do have any more questions, please leave them in the chat, and we can pass those on and get some answers for you. But thank you to Tom for joining us today, and I hope that's given everyone a really good overview of tectonics and volcanoes, and a little insight at what you might be studying if you take geography at university or at a higher level. So thank you for joining us today, if you're watching us live or on the recording, and we hope you have a nice evening.
Thanks all. Bye.